Hi, everyone. Thanks for being here this evening. A quick introduction to myself. My name's Rob Cowart. I am the creator of this solution that showed up on GitHub about 7 years ago, called ElasticFlow. And in fact, kind of speaking at Elastic Meetups, I guess, has a little nostalgia for me because I spoke at one in Munich about a few weeks before I spoke at one here in Switzerland about 7 years ago. Literally, I'll never forget it. It was about 40 degrees Celsius. And even with all the windows open, everyone's sitting there, which is pouring sweat and everything. But it was a good evening. And in one of those meetups, I was asked, I presented this experiment I was playing around with, which was taking network traffic records and putting it in Elasticsearch. And someone in the meetup said, "Hey, is this available for download?" And I'm like, "No, but I could put it somewhere." And I did, and I named the repository ElastiFlow. So fast forward to about 2020, and I knew there were about 30,000 instances of it being used around the world that I was aware of. And so I got together with a co-founder that was a better coder than me and said, probably a business opportunity here. And we started rewriting it because it was a science project, right? So we started rewriting it as production quality, high-scale code, and launched the company ElastiFlow about 3.5 years ago. We're now 35 people around the world, have won a number of large customers that use the solution together with Elastic, including quite a few here in Europe around that you probably would know of, but also around the world in various different industries. About half of our business is actually in the US, but about half is also in the rest of the world, including a few companies also here in Switzerland. So when I say speaking at a meetup is kind of a nostalgia for me, it's kind of like I always tell people all the time, speaking at a meetup, Nicholas was asking for volunteers. Speaking at a meetup, you'll never know when it'll turn into a life-changing experience. So as was literally the case for me. So what I want to do is I want to share a little bit today about some new features that were brought into Elastic over the last year that we have found super valuable and that have been really valuable to our customers. To do that, I want to kind of introduce you just a little bit to what the solution is. Don't worry, I'm not going to give you a sales pitch, but just to give you an idea of the data it is that we're working with and what some of the challenges of it are. So really the heart of what we do is analysis, collection and analysis of network traffic records. Now that can be on-prem or in the cloud. On-prem, that's really where we got our start. Those are technologies that are going to be in your router switches like NetFlow, SFlow, IPFix. It's essentially as traffic crosses these network devices, they can generate records that tell you who's talking to who and what are some attributes of those conversations. In a cloud environment, that'd be something like AWS VPC flow logs or transit gateway logs. Azure was mentioned in the last presentation, like the network security group logs, for example. So it's basically, again, who's talking to who and what are the attributes related to those conversations. And when you know that, there are a number of use cases that you can achieve that can be pretty valuable. Kind of the classic one is like performance and availability. So typical use cases here would be, the big boss calls from upstairs and says, the internet's slow. Well, you might look at it and say, well, yeah, the link's 100% utilized. Of course it's slow. But then the next question you have is, what's driving that utilization? Network traffic records can help you answer that question. We have a customer, actually used to be down the street from the old Elastic office, El Camino Hospital in California. They came in one morning and their network was pretty much 100% utilized. And what did they say? Well, what's causing that? And they immediately jumped into ElastiFlow. What they could see is, wow, there's a lot of traffic going from Google to our virtual desktop environment. And they had misconfigured something in virtual desktop, but they immediately knew the problem must be here. And 20 minutes later, they were back up and running. Now, we didn't help them solve the problem with the virtual desktop environment, but at least they can immediately get right to where that is. Another use case we see quite often is in this area of capacity planning and cost control. A real common one would be if you're on-prem, you're moving stuff to the cloud, you get that first your accounting team gets that first bill from AWS that it was all supposed to be cheaper and save you money, right? And they're like, what is this, network traffic egress charge? And you look and you go, well, let's find out what's causing that traffic. And you dive in, oh yeah, because there's like 3 servers we forgot to move to the cloud with everything else, and it's been sucking down data 24/7 and driving up the charges, right? So those type of use cases, and really relating to that previous talk quite a bit, where this type of data also gets used a lot is in security use cases. Because again, if you know who's talking to who and what are attributes of those conversations, there's a lot of interesting conditions that you can detect. In fact, when we sell our solution, part of that comes is over 120 machine learning jobs for Elastic's anomaly detection engine, alerts, with the MITRE ATT&CK stuff and all that, those same things that are part of it that you just import into the environment and you're up and running. And so the core of what we really do is we have our own ingest technology, our own collectors, if you will, that interface with the network or in the cloud environment for the network data, pull all of that in. We then parse it and format it, normalize it, and enrich it, and what we call translating, turning all these really obscure network things like TCP flags that, the raw data will tell you 23, and we say, oh no, that's like a SYN, an ACK, and a push flag, and that would lead us to believe the connection was actually established, and because that was between this service and this part of your organization, you probably care about that a lot, right? And so that's kind of how we take that raw piece of information and turn it into something with a lot more detail. Now, moving into kind of the meat of what I want to share with you tonight, which is collecting these records. If you think about, you open up a web browser, it's probably going to hit the website you went to, maybe hit a couple CDNs along the way, pull up some Google ads, and all of a sudden you realize you have like 15, 20 network sessions going on, and each of those is a flow on the network. Now multiply that by about 10,000 employees in a large organization, and you can literally have hundreds of thousands, if not a million, of these network traffic records per second coming in. And what starts to be the challenge then is how do you ingest all that and store all that data and keep it for as long as you'd like to have it? So really to understand the problem, we'll get into some math. Now, I do want to point out that all of our document size measurements here, when we made them, we put data in for a certain period of time. We did force merge the indices to make sure we had a consistent values that we were looking at, right? So y'all know what force merging is and all, and segments and things. We'll talk about them a little bit later too, because it helps to understand a part I'll talk about at the end. But so in this particular scenario, we were ingesting 32,000 records per second. So we had a test data set actually we were using for this. It's actually a pretty challenging data set. One of our customers is in the gaming space. In fact, there's one house in particular that probably most of you, if you game, have used. And when you log on and get authenticated and get your initial, like what games you have rights to and stuff, that's all actually handled by this one daughter company of this company. And they use us to see all that traffic. Well, they see about, on a typical hour, they might see 1.5 million IP addresses. Right? So it's a really high cardinality data set that can be challenging for a lot of data stores, as I'll mention a bit later. So that's this particular data set that we built this test around. 32,000 records a second on average with all of our features enabled. The records end up being about 572 bytes on average for that data set. So now you start doing some math. Okay, 572 times 32,000 per second times 86,400 seconds in a day. And what you end up with is about almost 1.6 terabytes of data per day. Now, if you got replicas, because you have high availability in a multi-node cluster, now we're talking almost 3.2 terabytes a day. You want to keep that for 30 days or 60 days or 90 days, you start to see how that can add up. So So at large environments, the great thing about Elastic is like we built clusters that are doing almost up to 3 million records per second. It is a solvable use case with the technology, but there has traditionally been a tax you pay on storage costs to have that ability, right? And so it can in some cases be a bit of an inhibitor, and so we wanted to solve that problem. So Elastic announced this thing back in, oh shoot, it's been a little over a year ago now where it first kind of came out, called time series data streams. Since y'all picked on Nicholas, I'm gonna pick on it too. I don't understand why y'all talk more about this. It's like one of the coolest things y'all done in our eyes for the last couple of years. And because it adds value in that it can save people real money. You know, if we take those numbers from before and now just look up what it costs to store a gig in the cloud, right? Or what you pay for a terabyte of storage, like it adds up quick into real money that you can save. So they released this feature, and so I want to dig a little bit into time series, what they are, how we viewed them in the context of our data, and what kind of some of our challenges were as we look to leverage time series data streams to greatly reduce the storage capacity requirements that our customers had. So time series data, plain and simple, it is for storing and serving or retrieving time series. So how Elastic implemented this is they leveraged a couple of features that they had for a while, which was I think it came out in Elasticsearch 6 was one of the features was sorted indices. So you long had the ability to sort an index based on certain fields. And then and that actually, and by the way, these numbers are our tests. They actually added their own numbers to the docs. I don't know, I want to say it was about 2 months ago, 3 months. And the numbers lined up almost perfectly. So I will tell you, independently tested, our 70% savings matches what they put in their docs as well. So I'm going to say, their numbers, not just some hypothetical, we wish we could get there. No, our testing showed exactly the same thing. About 30% of that comes from that index sorting. And then they introduced something called synthetic source. Are y'all aware of that? Anyone aware what synthetic source is? So there's a field in a document, underscore source, which is basically where the raw JSON document is done. If you've ever set the codec, there's like a default or best compression for your index. It's actually how you're compressing that source field, that original JSON. Well, what synthetic source does is it says, essentially, we're already storing the data when we create the indices. So it should be possible to just not store the original document, but recreate it from scratch based on the information that's in the indices themselves, right? And so essentially, there's a big chunk of stuff you're not storing anymore. Then you have that savings as well. And there's a few other things there. We'll talk about some of the other benefits in a minute. But one of the things that is really important and we'll get into is this thing of a routing path. So the objective of TSDS is to take all of the documents for a particular time series and store them on the same shard. A big reason why it wants to do that is there's a feature called downsampling. So the ability, there's long been this thing roll-ups in Elasticsearch. I always hated them. I always thought it was a terrible implementation. I apologize if the engineers listen to this recording. But what I didn't like about it is it changed the field names. So like if I said like, I want the sum of network bytes. And then the resulting field would be named network.bytes underscore sum. Well, now all my dashboards that were built for network bytes don't work anymore. So you'd have to modify everything to work. You'd have like your ones that worked on the rolled up data and your ones that worked on the raw data. And that's not very handy. What time series data streams brought was downsampling. And downsampling actually works the way you think it would. You can define certain fields, tell you how you want to do the math. It rolls them up, and it keeps those original field names. And this allows you to do things like, I want the raw data for 14 days. Then I want 5-minute aggregations of the data, maybe for 30 days, 15 for 90 days, and 1 hour aggregations out to a year, that type of thing. But the great thing is the way it's been implemented in time series data streams. When you downsample the data, it works in the dashboards exactly the same as the raw data does. So you will see some spacing, like if you have a chart that's only looking like an hour, and you have 15-minute aggregations, you'll see like 4 chunks at 15-minute increments, but you don't have to change any of your dashboards to be able to see it, which is really nice. So, the reason, though, that a time series gets put on the same shard is when you do those downsampling, it's a lot more efficient than to be downsampling by shard, if you will. So to support that, a time, and also to support quick retrieval, a time series. Remember, we're also sorting the indices is one of the features. So having a time series all on one shard has a lot of efficiency benefits to it. The way it determines where a time series goes is the setting called the routing path. And that was kind of the key to making this work for us. So, okay, let's just take a minute and just talk about time series. What are time series? So most people would tell you, especially if you listen to the time series database vendors out there, it's anything with a timestamp. Now, I don't know. I actually used to work for Influx Data back a while ago, so I'm going to pick on them a bit on here. Anyone use Influx Data at all? Right? So anything with a timestamp, you put logs in Influx DB? No, it's terrible for that. It's great for metrics, but it is terrible for those type of use cases. And so technically it's anything with a timestamp, but in real world implementations, it depends a lot on the qualities of the data store you're putting it in. So typically, though, a time series database is going to be made to hold I'll call it a finite or generally stable number of time series that are very long-lived. So, for example, CPU utilization on a server for the next 4 or 5 years until that server is decommissioned, right? So it's a single time series for a very long period of time. The other thing is you tend to have a lot of metrics and not a lot of tags, or as if you're a Prometheus person, call them labels, and in Elastic and TDS, they call it dimensions. But basically, those things that identify what the time series is, like take the CPU example, so like the server name, and maybe there's a CPU identifier, if maybe it's a multi-socket server or something, right? So those would be the labels or the tags that identify what that time series is. And then you typically are going to have some limit on cardinality. So, and we'll come back and talk about cardinality in a second again. But it's you're always at some point going to have some type of limit on how many instances of something, in this case, instances of time series you can have. And as I mentioned before, that gaming company, how many millions of they see in an hour, what they might see in a day. Then you get into what represents a time series. It can be millions and millions of time series for the thing. So let's look at network traffic flows, taking those qualifications. So do they have a timestamp? Yes, absolutely. Network traffic records have a timestamp. So we're in good shape there. Are these series long and at regular intervals? Not really. Like if I was right now to real quick jump over to LinkedIn. That's right. I'm in Switzerland. I have to say Zing, don't I? If I was going to go to Zing, or is that kind of dead now here too? Right. Okay. So if I was to go over to LinkedIn, and I look at a page and I close it out, man, that session, that TCP session to that server itself is kind of like the time series. So it is that session's over. Time series very short-lived, but I might have a lot of sessions. In fact, I actually tried using FluxDB to store this type of data, and about just a week of just stuff that happens at home, like people on their iPad or on their thing and surfing a little bit. I was already at like 150,000 time series. So, but they all tend to be very, very short things. Now, you might watch a Netflix movie and it's a 2-hour time series, but still relatively short in relation to what a time series database is optimized for. How about a few consistent tags, but lots of metrics that you might have? Not really the case either. We really have two metrics. How many bytes and how many packets were in the flow. That's generally, now some devices might implement other things, like there's some Cisco gear that might give you application response time metrics, or there's a few other things that could give you other metrics. But in general, you're talking bytes and packets. But you have a lot of tags, like source IP, source port, destination IP, destination port, protocol, class of service, which interface did it go into, which interface did it go out to, etc. Right? So you can have a whole bunch of these labels, and depending on the protocol, even more of them. But generally just two metrics. So that's kind of a bit of a challenge. And then comes the thing of cardinality, and I'm mentioning it yet again. That's the big challenge. So is it kind of limited cardinality? Not really. It's not even close. It's not unusual for us to have customers, if you were to think of it as just from a cardinality perspective, that could have millions and millions of IP addresses that they're saying. So you really have to have a system that can handle that degree of cardinality. Now, Influx Data did recently come out with InfluxDB 3.0, although we're still waiting almost 2 years for the open source version. That they claim unlimited cardinality. My general response was, yeah, well, release that open source version. We're going to put that to the test with some flow data, because I don't believe it. But that is the thing about Elastic that we actually that makes it great for this type of data set, because Elastic actually does a really good job of handling high cardinality values. The other problem that we had to solve is we had to say, okay, how are we going to assign these dimensions? What makes a time series, if you will, and that can vary based on protocol, as I mentioned. We did kind of settle on a particular set of those. I'll bring it in a second. And then finally, we had to get to that routing path, and that was kind of the part that made it work for us. So we talked about dimensions. We basically settled on this set of fields. Most of these I just mentioned a second ago. As kind of the core dimensions. Now, look, just because a field is not identified as a dimension doesn't mean you can't query by it. You can still get all the query capabilities that you would otherwise have and be really effective. Picking on our friends over at Influx Data a little bit, this is always one of the challenges with a traditional time series database like InfluxDB, is like, if you queried on the tags, man, it was really fast. But if you queried on a field that was not a tag, then it's just table scanning at that point to see if it has it, and the query performance just plummets. And so one of the benefits here is we get really great performance when we query on the dimensions. And if you're querying on another text field that's not a dimension, you just get pretty good normal Elasticsearch query performance. So either way, you're not really penalized if you don't make a perfect decision on this point. So we took kind of those core fields that would identify essentially a network session, and we leveraged those. Then, and this was kind of the hard part. So going back to the beginning when we first tested this, we first said, okay, we can this has a lot of promise. We saw the press release was actually like announced as a pre-release feature. We actually caught us off guard. You were talking about waiting on things. They actually said, this is tech preview. We're thinking, I literally thought, like, we got about 12 months until we got to worry about GA at least. Oh no, it was like 2 months later, it was GA already. We're like, oh my gosh, we got to hurry up. We want to get this support in. So when we first tested this, we built out one of our lab environments. We were pumping about 500,000 records per second into Elasticsearch, just normal Elasticsearch indexing to set a baseline. And then we did that on 4 servers, actually, by the way. If you want to know how we got 500,000 on 4 servers, that's a whole other meetup conversation. But so we were ingesting that, and then we said, okay, now let's turn on TSDS and make the changes we had to make. And it plummeted to like 125,000. Now the disk capacity, like the disk utilization was awesome. And we were like, all right, this is going to be sweet, but we got plenty of customers that have these higher data rates. That's not going to quite work. So we started digging into it. We're like, well, one of the servers is 100% pegged on CPU, and looks like the others are just chilling along, doing hardly anything. And what we realized is it was one shard was kind of the hot shard. And this is where the routing path comes in. So the routing path says it's basically a value or set of fields that determine what a time series is, and in other words, that's what shard it goes on to. And this is where you have to be careful when you want to implement this yourself, is you have to have enough variance in the routing path that the data can be evenly spread across all the shards you have available. In our case, the first thing we picked is, let's just say the device that's sending the flow records, we'll just use that. So each device that sends flow records will end up on a different shard. Well, we only have a pretty small data set, and one of the devices dominated that data set, which is why one shard was burning hot and all the other ones were hardly doing any work. So it had to be more complex than that. So what we had to sit back and think is, what is a time series in the context of network traffic? And ultimately, what we landed on, it's a session. Well, what defines a network session is very dependent on a protocol. So like if it's TCP or UDP, maybe even SCTP and a couple others, it's going to be like IP port protocol, source destination IP and port protocol. That 5-tuple, you could argue that defines a session. But what if it's ICMP? Or what if it's, another protocol? We're doing some work right now in with one of the hardware vendors in the US around networking for AI clusters. So, and there it's all UDP traffic to all one port to all, but it's embedded in that is like InfiniBand and something called RDMA over converged Ethernet. And so it's a lot more complex what defines the session in that context. And so what we realized is like, man, it's really hard to pick like a set of fields that is the routing key, because if traffic comes in from a completely different protocol, we could have a completely different set of fields. And I will give Elastic credit, they've actually increased the number of fields that can be part of the routing key. When it first came out, it was really small, which added to the challenge, but still, you have so many different potential protocols you're going to see in the network traffic. We had to have a way to define all of those possible session definitions. So here's what we did. In our collector, we actually wrote these protocol-specific algorithms that create a hash. So our routing path is actually one field. So we create one field, and that's the only thing that is that routing key, and that field alone determines which shard it goes to. And we make all the determinations in our collector, how that value is calculated. So ICMP has its own calculation. The RDMA stuff, Rocky V2 has its own calculation. VXLAN has its own calculation. Traditional TCP UDP, its own calculation. And that hash gets created, and that alone is what disperses it. So we did that work, boom, spread it out evenly. We lost no ingest performance at all. There is a little bit of, we'll talk about the negatives in a second, but no hit at all, and storage dropped down to 70%. So, or 70% reduction, so drop down to 30% of what you needed before, which is a huge win. So we actually have another customer in the US, Procter & Gamble, I'm sure is a company you've all heard of. That was actually a deal we did jointly with the Elastic team over there, going to ElasticCloud. Would have been impossible at the data rates they had without TSDS reducing the storage footprint in the cloud by 70%. So really great feature. And even if, like you gentlemen were talking before about the security data. Well, a flow record and a firewall log aren't that different. Got about the same values in it. Also, maybe some bytes and packets. Maybe the action the firewall took. This could be leveraged too for that same methodology and reduce that storage footprint. So there are some downsides. So let me share just a little bit about the environment we were testing on, just because I always think it's good when you share numbers that you kind of level set what it is, the environment we're in. So we're using an Epic 64-core processor, 250 RAM, NVMe storage. We did have Elasticsearch Kibana and our collector, just all on that one server. Let me bring up these numbers again that I showed. This is the same slide I showed earlier with those numbers on it. And then after using TSDS, so we'll just take a look at that almost 3.2 on the replicas. And we were able to drop that down to those numbers. So just to show you. So side by side, average size dropping from 572 to 177. With replicas dropping from for a day of data at that rate over 3 terabytes to down to less than a terabyte, less than a terabyte. Now, those are great results. Add real value, can save real money. Are there any downsides? Yeah, a little bit. By the way, as much as I picked on my influx friends, and then I throw up some charts that has some influx charts in there. But anyway, so as we were looking at our like the CPU utilization, we actually when this first came out, we were actually seeing about a 15% difference. And there was some work done even a little bit after GA now that we're probably down to about 7 to 8% more CPU utilization as the data is being ingested, because it has a little bit more work to do. Now, 7 or 8% more CPU in exchange for 70% reduction in storage, I think is a pretty good trade-off. Now, there was one other thing, though, that's worth mentioning. So we went into all of our dashboards, and we took the most complex query that we have, which is actually like 7 layers of aggregation in a table. So you have, an aggregate, so nested another aggregation all the way out to 7 nested aggregations. So it is our hardest query. And we took this measurement while we were actively ingesting 32,000 records a second onto the system. As y'all may be aware, if you're not ingesting data, I don't even care if you're on an old spinning hard disk. If you're not ingesting data, query performance can be amazing. But when you're ingesting data, there is quite a bit of impact, as it has to prioritize, Elasticsearch has to prioritize actually committing that data to disk. And it certainly has some overhead with it. So we took this while we were ingesting data. And you can see this query took almost 37 seconds without TSDS, but with TSDS turned on, it ended up being, a little bit over a minute. So it was quite a bit of an increase in that. So that was a little bit of a bummer. But not too long after that, Elastic came out with version 8.12. So, and they added this thing called query phase parallelism. Now, I mentioned segments earlier. So if you don't know, when Elastic ingests data, it writes the data into these things called segments, basically like a file system, if you will. And it's like the unit of storage of an index within a shard. And over time, as it writes new data, those segments get merged together. That's why if you ever like track write IOPS when you're writing data, actively writing data, you'll be like, man, that's doing a lot of writes. Well, it's because it's writing the data, but then it's rewriting it again when it merges segments together. And as more merges happen, it's actually doing more writing than you would think for the amount that you're putting in, but it's because of these segment merges. So what Elasticsearch has long been able to parallelize a query across shards. What it could not do was parallelize it across segments in a shard. And that's what this particular feature added. So I know these numbers are for non-TSDS, and we just missed grabbing the numbers before these slides were made, but I promise you it's a similar improvement also when you have when the shards are TSDS. But what we did is 8.11.4, which was the last 8.11 release before 8.12. We had that number I showed you before, the 36,759. We reran the test on 8.12, exactly the same, ingested the same amount of data, and ran the queries at about the same point. So we had the same history of data also in the system. And it dropped, just with two shards, it dropped to 29 seconds. So a noticeable improvement, no doubt. And we thought, What if we just increase that parallelism by adding a couple more shards? So we ran it with 4 shards, and wham, now we're down. We cut the query time in half. So what we felt was, if you remember going back to that previous slide, it was not quite double the time when TSDS was enabled on the queries, but with query-based parallelism, we kind of got right back and even slightly better than what the queries were anyway. So combining those two features together, we still had a net slight improvement in query times while reducing storage capacity by 70%. And it was just by thinking a little bit outside of the box of what time series data is, and then leveraging some stuff in our code, but also the way time series data streams works to achieve that level. Right? No, so that's what I was saying before. When we were doing all of our testing, we realized, oh man, we forgot to grab the numbers for the TSDS indices. But trust me, we've since done that. It is a similar improvement on TSDS as it is on non-TSDS. It was just you try to do these things so careful when you're doing testing, and we just forgot to record those last ones. So I apologize for that. But yeah, so that's it. Any questions?